So I was asked to speak about where are we with treatment-free beekeeping. And I think this subject is something that's actually just personal for all of us. Where are you in that scale? I think we'd all love to be there. We'd all like to have bees that just exist naturally, but it's not an easy thing to get to. So as I said, before I get to the topic, I'm going to go on a side trip to talk about queens and some things that are affecting queens. We heard a very nice talk yesterday from Italy about queen rearing and the importance of drones. And I'm going to follow that talk up with a bit of my own work about queens and queen quality. So, if you ask beekeepers why they're losing colonies, they'll say Varroa, but they'll also say queen failure. Queen failures are identified as one of the major reasons that we lose bee colonies. I can step closer. I was getting feedback. It's almost too strong. It's okay? Okay. And if we survey beekeepers and we ask them, what are the top 4 reasons you're losing colonies? This is some data from Canada, but you can see that many of the provinces in Canada selected poor queens as the primary reason that they were losing colonies through the winter. And it came in second and third in some cases. But poor queens is an issue if a colony doesn't naturally requeen or if the queen fails. So now I'm going to show you a study. We had identified these poor queens and we were beginning to investigate why queens were failing. And I'm going to show you a study that I did with Canadian colleagues where we looked at the effect of actually heat and cold stress on queens and how well the colony performed. And we do that, we heard an excellent talk about drones, and the drone mates with the queen early in her life, and she stores sperm in her spermatheca, which is a little organ in her abdomen. It's located about here. And they store sperm. This is a virgin queen, and this is one filled with sperm. We can sacrifice, kill the queen, and look in the spermatheca, and using dyes, we can tell whether the sperm is live or dead. And I'll show you some better pictures in just a moment. So we were getting a lot of reports from beekeepers. My colonies are failing, my queens aren't doing well. So we asked them to send us live queens from the east coast of the US or the west coast, colonies that were apparently healthy. So you take the queen out of a healthy colony, and nearby there's a queen from a failing colony. The colony's not doing well, so they sent us these paired queens, and this represents a number of queens from the east coast and a number of queens from the west coast, and this is the percent sperm viability. So this is about 70%, 85% live sperm is normal. You can see that the failing colonies had queens with very low sperm viability, about 50%, which is not good, which is not enough. The question is why? So, okay, now it looks like there's something about a failing queen and the colony performance, but why is the sperm viability low? And that's what we begin to investigate. So it could be, the drone's fault. There's a lot of things in the mating process, queen rearing and mating, where you need good, healthy drones, good weather. But there's also things when you get the queen mated and she's in a hive, you have issues of pesticide exposure, transportation. And then in certain areas in the US, we ship queens. We ship them through the mail to the beekeeper. And so we investigated temperature. We also investigated the effect of pesticides on drones. And this paper summarizes some of the pesticide effects on drones. And this paper of mine looks at not pesticide levels, but the shipping temperature. So we identified the shipping temperature as having an effect on sperm viability. So we know if the temperature is too high or too low, the queens are stressed and their sperm is compromised. So now we set out, okay, so what if they have a little bit of reduced sperm viability? We set out to do a field test where we would take the same group of queens, and some of them we would leave, we wouldn't stress them. This is about 88% viability. So this is high viability in our controls. They were held at 25C. And then we heat stressed and cool stressed for just 1 hour each. And you see reduced viability. So this is, we sacrificed a number of queens that were part of the experiment, but that we didn't put in colonies as controls early on. And now we have 60 colonies. 30 have heat stress queens or cold stress queens, and 30 are controls. And we're just going to follow them through the season to look at the effects of this heat and cold stress on the colony productivity. This is the way we look at sperm viability. We do have to sacrifice the queen. We open up the spermatheca, and we use 2 dyes. If they dye red, the sperm are dead. And here, this is the head of the sperm, and they're live. The green is live, and red is dead. So it's a very easy technique to do. You do need a special microscope. Okay, 60 colonies, all in the same apiary, and we're running them through a Canadian summer. And the Canadians produce a lot of honey, by the way. This is in Alberta, very good beekeeping area of Canada. We looked at the brood pattern. So we count the number of missing cells, and this is 100 cells. And here we have a poorer pattern, and here we have obviously a very poor pattern. So we look at the brood pattern over the season. And this is assessment 6. We assess them about every 3 to 4 weeks. So late in the summer, the average here is about 60%. So there's 40 cells out of 100 were missing. And here it's above 80. So this is a type of brood pattern we'd see in the controls. And this is an extreme example, a real poor example of what we see in the brood pattern. So we saw, obviously, poor brood patterns. We looked at honey production through the season. And the controls produced, on average, about 50 kilos, maybe a little more, about 50 kilos. Look at the temperature stressed. They produced 2/3 less honey, in part because they had lower adult bee populations. With that bad brood pattern, the population of bees in the colonies was less. What's even more important than honey production? Survival. So we then took these colonies and went through the winter. We started with 30 in the apiary. At the end of the summer, we had 23 queens in both groups. We'd lost 7. So 7 out of the controls and 7 out of the temperature stress. So we're going into winter with 23. And here we are in the fall, and look what happened the next spring. In the spring, the temperature stressed, we came through with 9 colonies, whereas these 23 colonies survived into the next spring. So it was a dramatic effect on honey production and colony size, and then those colonies headed by temperature stress queens, the vast majority of them, over half, died through the winter. So again, we saw a number of effects from simply having good viability in the queen, or these are different temperatures that we stressed them at in the experiment, where you reduce the viability of the sperm in the queen, it does have a colony level effect. It impacts brood production, it impacts the honey production that colony does, but for me the biggest effect was that then over half of those colonies died through the winter. So the take-home message is we need to protect our queens. I mean, yeah. And I just want to thank, this was primarily headed by Dr. Martha Guarna and Dr. Steve Pernall. They're both at Ag Canada in Beaver Lodge. The National Diagnostic Lab in Alberta helped, as did Dave Tarpey in North Carolina and myself. So it was a very big collaborative effort to try to understand what this heat stress or cold stress could do to queens at the colony level. So now I'll ask you a question. In your own beekeeping, I can think of one thing that you can do to avoid almost all of these things. And actually, I'm not going to answer it yet. I'm going to leave it to the end of my talk. So there's one simple thing in your beekeeping operation that you can do to avoid many of those problems. And I'll leave that question for you to think about. So now to the subject I was supposed to talk about. Where are we with treatment-free bees? As I said, I think we'd all like to get there. We don't enjoy fighting Varroa all the time. And I'd like to show you the outline, some of the things I'll talk about. Bees can naturally survive, and I'll talk a little bit about where they're surviving naturally. And I'll give some examples of that. I'll talk briefly about the potential mechanisms of resistance. There's a lot, when people are breeding for Varroa resistance, they're always trying to understand the mechanisms. How are the bees fighting off the mites? And then I'll talk about how can you select, or how can we select resistant bees. So, most of us are keeping bees in a northern, colder climate, northern hemisphere. If you think about the vast majority of the southern hemisphere, they don't treat for Varroa, and yet they have Varroa. Most of Africa doesn't treat for Varroa. Latin America, South America doesn't treat for Varroa. They have a kind of a hybrid Africanized bee. As you get further into Argentina and it gets colder, they begin to have to treat for Varroa. So Varroa and the effects of Varroa, there's two things going on there. One is the temperature, the fact that our bees have to go through a winter. So any additional stress is going to reduce the winter survival. But the other thing is I'll call it the type of bee. More tropical bee, African bee, or more, they seem to be able to deal with Varroa. How are they doing that? That's where people get into the resistance mechanism. What mechanism are the bees using to fight Varroa? This is an example in North Africa. Bees kept in, traditional hives, clay hives. They swarm a lot. That seems to be a feature that helps bees fight off Varroa. They swarm, they break the brood cycle, and the Varroa go down. We don't always all want to keep bees like that, but we could. So Varroa came from Apis cerana, the Asian honeybee. And this is just a few pictures of hives of them being kept in Asia. They do keep them in traditional hives. They keep them in movable frame hives as well. But to try to understand how Varroa is affecting our bees, people have gone to Asia and tried to look at how Apis cerana, Asian bees, are dealing with Varroa. And what they do is they reproduce almost exclusively on drone brood. So if you look in an Apis cerana colony, you'll almost never find Varroa in the worker brood, almost never. And why is that? And some of my colleagues and I, we talked about that if we understood that mechanism, we call that the holy grail of understanding resistance. Well, guess what? We now know what the holy grail is, but it doesn't help us. I'll show you that in a minute. So we got the answer. We got the answer. This is how Varroa is dealt with by Asian honeybee. And the answer is in this paper. This is supposed to wake you up. When Varroa, very simply put, when Varroa invades a worker cell in Apis cerana, the brood dies. Full stop. So if a Varroa, in this case, kind of makes a mistake, and it's walking around trying to select a cell to move it, and it moves into a worker cell, the developing larvae and pupae die. So that's huge pressure, and the mite dies with it. So that's huge pressure for the Varroa not to infest worker brood. So we don't have any evidence that that happens in our bees, Apis mellifera. So we understand now how Asian honeybees fight Varroa. They only reproduce in drone brood, so it doesn't affect the colony. But understanding that mechanism is not really helping us in Apis mellifera in our bees. What happens in our bees? What happens in most situations in the northern hemisphere? This is the bee population, kind of a stylized bee population. It goes up, it goes down a bit into the fall, but the mite population almost always builds through the summer, and without treatment, it's going to go really high in the fall. That's why perhaps we treat in the early spring, or perhaps we treat midsummer right in here, and then we follow up with a fall treatment. So in our bees, the Varroa almost always build through the summer and peak in the fall. But if bees are naturally existing with Varroa, what are they doing? What are they doing to keep this from happening? That's the question. How do they keep mite levels low? There's a whole host of behaviors that people look at. Hygienic behavior, you heard about it yesterday. It works well to combat chalk brood, American foul brood. It's just the cleaning out of diseased cells. VSH, Varroa sensitive hygiene, is a special focused hygienic behavior. They detect the Varroa in the cell and they remove it. And there's a lot of work going on VSH, this type of hygiene. Part of that is what we call recapping behavior. The bees uncap and they sense something's in the cell and then they recap it. And when they do that where Varroa is present, they disrupt the mite somehow. So there's recapping behavior. Bees can groom the mites off. They can bite and damage the mites. There's some work going on with that. Worker development time, this was proposed for the African bees. They thought they'd develop faster. They don't produce as many mites. It probably has a minor effect. And then this is a new type of defense. It's being premiered here. You've never heard of this before, but the bees actually do use a COVID defense mechanism. And I bet you haven't heard about it. So, but you're about to. So, yeah. So the hygienic behavior, right? You've seen these pictures. They clean out the cells, et cetera, et cetera. What is the COVID defense of bees? It's colony overall Varroa integrated defense, COVID. And it's kind of a joke, but it's not. It's actually, this encompasses everything I want to say about Varroa defense. And it's because I don't think we need to look for one mechanism. I think when you let bees go, and I'll show you some examples, the Gotland bees you probably heard of in Sweden. They put 200 bees on an island, 200 colonies. They died down to 40 or so, and they keep building back. What mechanism were they using? They were using probably a little bit of everything. And that's what I'm trying to get at with this colony overall Varroa integrated defense. They're not using one mechanism. I'm sorry. I'm sorry if I offend some of the queen breeders and some of the researchers that are focused on VHS or whatever. I think the bees are using a number of mechanisms to combat Varroa. But anyway, this is just something of my own imagination. So what are some of the true mechanisms that we can look at? I've already touched on these. And again, hygienic behavior is just a general cleaning behavior, chalk brood and American foul brood, Varroa sensitive hygiene, and there is a lot of excellent work going on understanding this mechanism. It seems to be one of the dominant mechanisms I say it's dominant, it's not the only mechanism. This is recapping behavior, and it's been talked about recently, some papers by Melissa Oddie and Steve Martin and others. The bees uncap and look in the cell, but they don't remove. They don't remove the contents. And then they recap it. They close it back over. And this is I mean, it's hard to see in the back of the room. This is a normal capping. It's all light in color. And down here is the normal light color. And here's the patch. They patched it back over with some darker wax. So we can look at that. If we look in the cell that's been closed over, we can tell if it's been recapped. And something about this recapping disrupts the mites. And we know that certain populations, the bees in Norway that are fairly resistant, seem to have this recapping behavior. Bees can groom, and they can bite and damage mites. And this is well known in a variety, and some people are selecting for bees that do better at grooming and biting. They damage the legs. They often damage the legs, or they can actually bite and damage the exoskeleton here. This is an undamaged mite with a nice circular pattern, and here they've bitten the mite, and it's fallen to the bottom, and it dies. So, again, this is another mechanism that they can use. But if you think about a bee colony, why would it focus all its efforts, and why would it only do one thing? It's not. It's doing multiple things that I think we don't fully understand. This is something that we as beekeepers do. We make divisions or splits in the spring. That lowers the population of mites. So if you take a nuke or a split out of your colony, the parent colony will have lower Varroa, and the nuke will have lower Varroa than if you left it alone. So making nukes helps reduce Varroa. The bees do this naturally. They swarm. So it's very similar to swarming. That's a cultural control. So how could you, as a beekeeper, begin to select, if you don't want to get into and look at all these specific, resistance mechanisms? Well, there's a nice paper published by Blackier et al. Not too long ago where he called it Darwin's black box. All you have to, and you'll hear more about that by our next speaker, but basically, you don't have to understand the mechanisms. You just have to challenge bees with mites and look at who survives and breed from the survivors. So you have to let the Varroa challenge and let some colonies die, and then challenge and breed from the survivors. You actually don't have to let them die. You monitor the Varroa, and when the colonies where the Varroa build up, you take them out of your operation. You treat them or something, but you don't breed from those. You only breed from the ones that keep Varroa low. But you don't have to understand the mechanism. You simply know that they're doing something right. So you'll hear more about that in a minute. These are just some examples from around the world. Left alone, bees can survive. And this is all Northern Hemisphere stuff. So I told you a bit about the Gotland bees. Ingemar Fries called them the Bond bees because he just put them out there on the island and said, live or let die. And it was successful. You've read papers and talks by Tom Seeley. He studied bees in this Arnott forest in New York, and they were at a certain density, so many colonies per hectare, and he thought they all died out. But when we went back 15, 20 years later, actually the bees were back in the forest. They had rebounded. And he doesn't understand the mechanisms, but he talks about small cavity size and swarming, things like that help these bees survive. And this is an example of just a wild colony. And then there's the French bees, John Keefus, Yves Leconte, and others. I had the opportunity to work with, not with the Arnott bees, but with the French bees and the Gotland bees. The French bees were a little excitable, shall we say. They were, I wouldn't say they stung a lot, but they were nervous. They were kind of excitable. The Swedish bees, actually, it was pretty amazing. Going through the winter, they kept small colonies, but going through the winter, they would reduce to 1 to 3 frames of bees. And you think there's no way 1 to 3 frames of bees is going to make it through a cold winter. And yet in the spring, they're there on 3 frames or 2 frames, and slowly, slowly they build back. I mean, it was amazing. I don't think those bees are particularly good, you know, for the average beekeeper. The French bees are good, and the bees I looked at in Norway that also have resistance are good commercial bee. They tend to do everything we want a bee to do. So these are just some examples. Now I'll switch a bit and talk about a population of bees. I'm working with Colonies, a nonprofit out of Paris, and we're working on Ile de Groix in Brittany, France, on the coast of France. And there's a population of Apis mellifera mellifera bees there that are fairly pure, Apis mellifera mellifera, the dark bee. And they seem to be surviving quite well, and yet there's managed bees on the island, and there's wild bees on the island. And it's not a very big island, 3 or 4 kilometers wide by 8 to 10 kilometers long. It's not a big island. So we're doing a number of studies to try to understand how these bees are surviving without treatment. That's the other thing, without treatment. It's kind of a 3-way partnership. You'll hear from Dr. C in a minute. And this is the primary beekeeper, Christian Bargan, and Nicholas from Colonies. And this AthonGX is the association to preserve the dark bee en Groix, basically. And the beekeepers there's many different ways to keep bees, obviously. The beekeepers en Groix, they don't feed. They let the bees build natural comb. So they do like this. And these are bees, this is Colonies en Groix. And so they practice a kind of sustainable, hands-off approach to beekeeping. It may not be practical for everyone, but it works really, really well for them. They don't interfere much in the bees' progress. They don't monitor for mites. They don't treat for mites. They don't feed. And you'll hear a little bit more about the mite numbers from our next speaker. So the first thing we did was look for Varroa. So we do a sugar shake and look for the Varroa. And we've done that over 2 years. And as I've spoken earlier, the Varroa should build up in the fall, and I'll leave it at that. But it's a nice place to keep bees, and there's managed and wild colonies, and we're following both of those and their survival rates. And this is just to reiterate this part. We expect the mite populations to build in the fall. The other thing that's kind of interesting, and I apologize, you won't see it that well in the back. This is not all Varroa. It looks like Varroa. This one right here is a Braula. It's a bee louse, and you don't see those very often. They're 6-legged. It's a little fly that lives in the colony. There's one there, and I believe there's one there. But it's a small parasite. Doesn't affect the colony much, but it lives in these colonies, I think, because they're not treated, so it's able to survive. And this is just a picture of the island itself, and we're monitoring all the locations where the wild swarms are living on the island and monitoring them over time. The number of colonies and the survival rate. And we'll have more to say about that at a later date. But the bees are surviving, the wild bees are surviving, and the managed bees are surviving. So, possible resistance mechanisms. Again, I think what bees on Ile de Groix are using is some combination, whether we call it COVID defense or whatever. I don't think they're using one mechanism. I doubt it. I don't think they've been selected for VSH trait. They've been selected to survive. And it's been natural selection. Am I going to do that with my bees? I'm doing it on a limited scale, and I'll say a bit about that in just a moment. So I think the bees on this Ile de Groix, the bees in the Arnott Forest, and things like that, they've gone through this natural selection process. Which brings me to what type of bee should we be keeping? This is kind of a stylized map of the different subspecies of bee in Europe. Apis mellifera mellifera, the dark bee, should be in France, England, and up into Germany and Scandinavia. I call it the Spanish bee, Iberica, is a bee that was historically in Spain. You know Ligustica, I mean, people breed Ligustica, it originated out of Italy. And then Intermissa is a North African bee. My reason for showing this is a couple of fold. One is bees adapt to their environment. They definitely adapt. I know a number of you are keeping Carnica. Carnica is an excellent cold weather bee, right? It's very gentle. What happens if you move Carnica into Africa? It's going to die. I mean, it's just not going to survive. It's not going to do well. The same if you try to keep Intermissa in Sweden. It's just not going to survive. So local adaptation has already happened. It happened before we interfered with it. And now we need to, in your own operation, you just need to look for those bees that do well in your area. But I'm also making a plea for one other thing, and that is we need to work. I don't think anyone would oppose if we had some pure breeding areas for Carnica in Slovenia or here in Austria or somewhere. Like we kept a little isolated breeding place for Carnica. The same for Ligustica. If we have these little isolated pure breeding areas for Ligustica. But no one's going to speak up and say we need to keep these breeding areas for Intermissa or Iberica. No one's going to go, yeah, we need that. I mean, there are people who are doing it, but I would argue that we still need that. And I know that comes into conflict sometimes with commercial beekeepers, that they say, well, if you're setting off that area, then we don't have access to it. But I would argue that these areas that we want to preserve for mating, isolated mating and for pure mating, even if it's Iberica or Intermissa or whatever, in those areas where it naturally exists, we should do that. And I know there's a lot of people that are trying to keep pure mellifera mellifera. Is it the perfect bee for everybody? No, but guess what? It is the bee that should naturally be here. So that's just a plea on two fronts. One is that's the bee that developed in Northern Europe, and it's the bee that works well in Northern Europe. So, conclusions. Bees can survive. If we leave them completely alone, some bees will survive. And we don't have to understand all those mechanisms. We just know that even in the pressure of Varroa, they will survive. We can let nature take its course. I do think we need to preserve diversity of the different subspecies in different areas. The commercial beekeeping, and I'm not commercial, but I'm a sideliner. I'm not treatment-free, and I'll show you a couple of pictures, but I'm breeding from my best surviving stock. So I think for commercial beekeepers, there's a longer transition time. These are my own bees. On the east coast of the US, I manage about 125 hives. I keep them in a single Langstroth deep box, and I do use queen excluders, and then I put on honey supers. And I'm not too concerned about swarming. I try to make nukes, but I don't aggressively stop swarming. I let them swarm if they're going to swarm. And then my son and I, and my wife as well, we do collect and sell honey, and as I spoke earlier, we sell at local markets, so we control the whole stream. We get all the thing, and plus the people know us. They can trust it. It's local honey from local beekeepers. So back to my question. So what do you think you can do? What's the one thing you can do? Like I talked about temperature stress and things that can affect the queen. There's one simple thing that you can do to avoid any of the queen issues that I've talked about. If you have the ability, you just breed your own queens. If you can breed your own queens and they never have to be in transit, that's a good thing. You can also buy cells. If you buy mature queen cells and make nukes, then the queens mate in your own yard, and they mate with drones that are adapted to your local area. So anything that you can do to breed locally or use queen cells and let them mate in your yard will get you further down the road. There was something else I was going to say about this, about the breeding locally, and now it escapes me at the moment. But yeah, it's a simple thing. And again, you're in a good position. If you look at 10 of your colonies, you know which ones are performing well. And I would encourage you to also do some sugar shakes and look at the Varroa levels and work with the ones that are keeping the Varroa population low. So before I go there, so can you get to treatment-free? Yeah, you can get to treatment-free, and you can take the hard road, which is like the Gotland bees, and just lose a lot of colonies and select from the survivors, and you'll get something. I think a better approach, I've got a couple of different resistant stocks, VSH and others, that I brought into my operation, and I'm just letting everything mix, and I'm doing my own selection and grafting queens to keep my own bees going. So I'm doing my own selection within the stuff that I brought into my operation. So I think it is possible, and I think we'd all like to get there. Whether it works for you is another issue. But I think treatment-free beekeeping is an option. I know people that are doing it all over the globe. It's a lot easier in the southern hemisphere than it is in the northern hemisphere. Okay, so with that, I'm going to close by just, oh, and I didn't update my slide, but that's a COVID-related thing. We would already just be coming back, had COVID not hit, we would be just coming back from Ufa, Russia, after a successful Apimundia meeting. In 2021, we moved it 1 year. So we're now holding this meeting in 2022, in the fall of 2022 in Ufa, Russia. And I invite you to attend this meeting in Ufa, Russia. If you can't do that, there's a meeting in 23 the next year in Santiago, Chile. And then 2 years after that, we'll come back to Europe. And I think the leading contenders are, it'll be bad, but I think Poland is going to bid, Italy's bidding, and the Scandinavian countries, Sweden and Denmark are bidding together with Norway. So there'll be an announcement about where we're coming back to in Europe. It's a good opportunity to meet beekeepers from all over the globe, maybe to hear about some of their successes and failures and stuff. So with that, I'll close, and thank you.